And again, I won't, these are the Kalman slides. I won't go through these since Dr. Wan already talked you through the Kalman filter recursions. There's different ways to present it. If you look in a text or a paper on the, you'll find they may be than what you'll see in slides as well as his. It shouldn't scare you. It turns out that there are mathematically equivalent forms of the Kalman filter recursions. There's more than one way to present them. Here you talked about the ends, the state error points. That's the hardest thing to derive. And then this is one flavor of the Kalman filter recursions. And again, this should be enough to code it in. And I know Dr. Wan made gave a lot of insight as to what's going on with these equations and what some of the different elements mean. Prediction updates and updates. And then this is the example that I wanted to go through. Years ago, when I was teaching a class like this, I had a student that was working on the rocket that Jamie presented on, and he wanted to estimate the position based on the accelerometer from the rocket. And I thought, it's great, that's a perfect application, it's linear, and that can work really well in this example. That was before I knew much about accelerometers. I know a lot more about them now and their limitations. So the statistical, let's see, this is a little bit, off. It's hard to talk about a white noise process in continuous time. I don't know if Dr. Jenk talked about this in his signals and noise class, but here I've got, this is supposed to be a white noise process, but it's in continuous time, and I'm saying that the derivative of the position is equal to this white noise process. But it's hard to even define that. It's much easier in discrete time to talk about what a white noise process is. In continuous time, I think technically a white noise process would have to have infinite bandwidth and therefore have infinite power. And they just don't exist. And the math of those processes gets fairly complicated. So what we usually do in discrete time is we just assume that when we sample it, the sample rate and the bandwidth of the noise is such that from one sample to the next, the samples are uncorrelated in time. And so I'm hesitating because I'm seeing this expression, and that goes into a topic that I hadn't intended to go into. And then for the measurements here, I'm assuming what we can measure is the output of the accelerometer. This is ignoring gravity for the time being. So we get a measure of the second derivative of the position with respect to time plus some additive noise. And one of the things that's different about this, when we think about modeling a random process, the common approach when you're working with some hopefully this won't slide out. The common approach is to say that your acceleration, which I'll denote x double dot time n plus 1, is either a random walk or a white noise process. And so this, the acceleration, I tried to put two dots on top of it, is equal to what it was, let's say if we use a random walk process, plus some noise. And then to get the velocity of the process, we say x of n plus 1 is equal to essentially the discrete time equivalent or approximation of an integral of the acceleration signal. And so we say that the velocity is equal to what the velocity was, plus, and then this is just a piecewise constant approximation of the integral over the sampling interval, ts times the acceleration. This should have been x double dot here. And so we've got a random walk process that we've used a number of times for the acceleration, and then the velocity is equal to essentially the integral of the acceleration, and then the position we usually say is equal to just the integral of the velocity. So the position is equal to what it was plus t sub s times xn. And if you're in multiple dimensions, this can get a little more complicated, but the idea is essentially the same. So this is the common approach for modeling. And one problem with this is it creates a lot of potential variability in where your position can be. Your position can now grow if the variance of a random walk process grows linearly with time, then your position can grow cubically with time. And that may not accurately represent the dynamics of your process or how whatever it is that you're trying to model actually moves. And so as an alternative to this, I used a slightly different model in this particular example. And was there a question, Reed?
You're just missing a dot, that's all.
Oh, yeah.
The bottom equation, TSX sub n.
Thank you. Huh, it's not working so well. Yeah, thanks. This is one of those cases where I don't know if I should go backwards or not.
Isn't a good model for the rocket, or?
Well, I chose, at the time I steered the student towards a different model, and I argued it was better. And I wouldn't have done that now, but I wanted to talk about the differences because I think it illustrates some of the different approaches you can have towards modeling. What I steered the student towards as an alternative is a random walk model for the position instead of for the acceleration. And because our measurement is still in terms of the acceleration, I needed a way to relate the position estimates to the acceleration. And so what I ended up using, and what I'll show in this example, is that the position here can grow, is a random walk model. The position is equal to what it was plus some random noise. And then I've got delays here, delayed versions of what the position is. So I've got the position at time n is equal to essentially the position at time n plus nothing, and the position at time n minus 1 is equal to the position at n minus 1 plus no noise. So instead of using integrals, or the equivalent of discrete time integrals, in this example I created delays, and based on those delays you can get a sort of simple approximation, discrete time approximation of the acceleration based on these coefficients. I derived that 2 slides earlier, but again I don't want to confuse things by going back in time. But this is, with some fairly straightforward math, the equivalent of doing the derivative twice on the position signal. And so you end up with this being the acceleration is related to the position in this way. And it's a different model. And the assumptions are quite different, because this says that if we've got a random walk process on the position, that's equivalent to having a white noise process for the velocity. The velocity from one sample to the next under this model is unrelated. And the acceleration is the derivative of a white noise process, which just simply amplifies the high frequency power and has very little low frequency power in the estimated acceleration. So it's just a different way of modeling the process. And you could do something in between where you say, well, I'm going to use a random walk model for the velocity or for something else. So there's a number of different ways of doing this. And I guess the main point I wanted to convey with this example, one of the main points is just that you have more than one choice in how you go about your model design. And the model design is really key oftentimes, especially for your state model, for being able to represent the prior knowledge you have in an accurate way. And I'll say more about that with another example on with inertial sensors on Wednesday. So at the end of this, we end up with a simple linear state model. I think in Dr. Wan's presentation, he used U to represent an external input. In this class, I'm always using U to represent the noise, and I usually don't multiply it by a matrix. I should drop the G. That's just a not exactly a notational error, but a leftover from when I was using a slightly different notation.
You needed it this time, though,
The G. Well, I didn't. The way I would have preferred to represent this is where U is a vector, and the covariance is mostly 0 because you've got zeros here, and there's only one element there. So it could have been done even without the G. But that's a good point, Jamie. I mean, maybe it's a little bit easier, a little bit simpler, representing it in this way with G, where U is just a scalar. I don't think it makes a lot of difference. And then this is we've all done a lot of simulation runs, all worked with synthetic data. This is synthetic data in this case. And again, I'm ignoring the effects of gravity, so you can imagine an accelerometer operating in a horizontal plane for now. I'll talk about a more complicated case on Wednesday. So this is the measured acceleration, which is just calculated directly from the position and creating synthetic noise in the way that we're used to. Let me know if you have any go through this. And then this is the other thing that I thought was really cool about this example is the assumption is that you know what the starting position is essentially perfectly. So there's very little uncertainty to begin with. And this is a case where as time goes on, you have growing uncertainty about the position. And in fact, you can see that I think this is a 95% confidence interval. You can see that it grows with time in the way that you would expect. A random walk process has variance that grows linearly with time. And so the standard deviation, which is proportional to which is what these confidence intervals are proportional to, will grow with the square root of time. And that's why they're a little bit curved and they're not linear. It's because we're looking at a standard deviation rather than the variance or something proportional to a standard deviation. And so we start off with really good knowledge, and it's able to track really well, and then pretty soon after a while, it's gone far enough, we're measuring acceleration, and there's an accumulated error that we just can't track. And so after a while, it just steadies out and becomes more or less constant, is what the Kalman filter produces as an estimate. But the confidence intervals representing the uncertainty or the state error covariance continues to grow. And I think it was Eric that had a way of inverting the measurements to get a naive estimate or sort of a crude or direct estimate of the state. And in this case we can as well. If we're getting the accelerometer with noise, we could integrate it twice to get an estimate of the position as well. And that's what I've shown with red, just as for the sake of comparison, so we can see what would happen if we did that, and is that any better? And as you would expect, the variability of that estimate increases with time. It doesn't become steady after a while in the same way that the Kalman filter estimate does. Sam?
The red curve would be the mean of the likelihood function. Is that like one way about the red curve?
I think that's equivalent. Well, it's not quite the same because we're not measuring the state directly. We're measuring a linear combination of the state. And so if you were to look for a maximum likelihood, it would give you an estimate of the vector at a given time. And I think that's a case where at any given time, if you're ignoring the state dynamics, at any individual time there would be multiple solutions because you've got 3 free parameters and 1 constraint. The measurement is scalar in this case, whereas the state has a dimension of 3. And so I think maximum likelihood in this case, this is an example of maximum likelihood would fail because there's many, many solutions that are equivalent. So that in this case, that wouldn't work. Any other questions or comments on this? I like this because you can see the growing uncertainty, and the Kalman filter does something very reasonable where it tracks closely for a while, and it realizes there's so much uncertainty that it just goes steady, and I thought that was intuitive and appealing. And Franco?
Sorry, I didn't catch. Could you just spend a few words again on what the naive estimate, where the naive estimate comes out?
Sure. So what we're measuring, y of n, is approximately equal to the acceleration. And so the naive estimate, the way that I calculated it is I essentially took y of n and I integrated it twice. Rather than representing that as a sum, I'm just going to abuse notation and write two integrals of the continuous time equivalent. And this would be 0 to whatever time we're at, the current time, and this would be 0 to the current time as well. There's some complications there. I should be more careful on the limits and whatnot, but basically I'm just taking the measurement and integrating it twice.
That's what I needed.
Yeah, okay, good. So when you're thinking about modeling the dynamics of your process, think carefully. And once again, one of the beautiful things about the state space methods, all the state space methods, except the Viterbi algorithm, is that they give this indication of how much uncertainty you have about your state. And that's really, really nice and appealing. It's something you don't usually get with most. Yeah, it's just another run. These numbers didn't change, 1, 10, and 0.1. This just shows another example. I don't remember if I changed the parameters. I think this is just another run, although I'm going to 1, 10. So in this case, the naive estimate, goes completely outside the confidence intervals, and the actual position in this case stayed within them over the entire duration. And yeah, this is just a run. And in this case, I increased the variability, and I made it stable. So this is, instead of being a random walk process, now it's an autoregressive process where the state is equal to 0.99 what it was. And that, as soon as you cross from 1 to a number less than 1, you cross from modeling it as being non-stationary, random walk is a non-stationary process, to suddenly being stationary, well, at least stationary asymptotically. The uncertainty grows with time, but it reaches a steady state. And so after a while, the confidence intervals remain stable over time. And the average value of the estimated position stays pretty close to 0, although it doesn't become exactly 0 in this case. So that's a significant change. And it's cool that it still does some degree of tracking, although it doesn't get very far from 0 in this case, because there's a bias for the state to be towards 0 as soon as you make that less than 1.
It's interesting that the naive approach works very well at the beginning, and then at some point then it goes holistic.
Yeah, but there's not very much measurement noise in this case, and so initially there isn't an accumulated error, but by double integrating, any error that you have here accumulates with other error from further back, and it grows pretty rapidly. So I guess after you think about it for a while, you're like, oh yeah, that's what it has to do. But yeah, it is neat that it does that. This is just another run, I think, with the same parameters. Yeah, 0.99, 10, and 0.1. I did 3 of each. Okay, and then one other example I wanted to show you. And this is really cool. I mean, I think about the Kalman filter, and I think I've told this story before. When I was first taking a class on the Kalman filter, I thought, what a waste of time. No one's ever going to give you a state space model. How could this ever possibly be useful? And little did I realize that if you think about it just a little bit, there's a number of ways in which you can use it. This is the way in which I've used the Kalman filter the most, is as for modeling an autoregressive process. And with this, you have a very powerful, very useful adaptive filter that you can sort of get your hands around and use for a number of different applications. The idea here is, and I don't think I've got the equations, so let me write them here. With the autoregressive process, that we have in mind is that y of n is equal to a sum over some number of elements. I'll use L is equal to 1 to, let's make this n sub x of, let's call it x of n, because I'll put it in the same form, y of n minus 1 plus some noise. Now, for those of you that have taken a lot of signal processing classes, if you, instead of thinking of this as a state variable, if you think of this as a coefficient, say a fixed number for a minute, then you'll recognize y of n is equal to some linear combination of past values. This shouldn't be n minus 1, it should be n minus L. Some linear combination of the past values of what the process is, and then there's some noise that's driving it. Now, this is, when y of n is equal to a linear combination of past values, that makes it an autoregressive process. And if it's driven by what, I need to be more clear. This is an IIR system that is being driven by white noise. And it only has poles because y of n is only equal to some combination of what past values of the measurements have been. And the big idea of how the Kalman filter can be applied to this is, instead of thinking of these as a set of coefficients, maybe that you have to estimate from data, instead to think of these as the state variable. And that's why I've written it this way, where the state variable is the coefficients. You may not know what the coefficients are, you may want to model a process, you may want to do prediction. Notice that this is doing prediction of what y of n will be based upon what past values are, is one way of thinking about this. So you can use this for one step ahead prediction. It turns out that if you know what the coefficients are at a given time, it's very easy to figure out what the power spectral density should be of y of n by just doing a discrete time Fourier transform. So it turns out there's a lot of things that you can suddenly do when you model any process in this way, and you're interested in doing spectral estimation, one time step ahead prediction, or you just want to statistically characterize the process, and everything is then captured in the coefficients. When you do it this way, usually the coefficients, you don't have any idea what they are, and so a random walk model is used to let them adapt. And the main knob you have, you think, well, shoot, if I've got a process, I have no idea what the variance of the measurement noise is, and I've got no idea how quickly I should let these parameters adapt. In other words, I have no idea what the process noise should be. And if you go through and do a lot of math, with the Kalman filter, you can show that in the case where the process noise is some number times a diagonal identity matrix, you've got the same process noise on everything, and your measurement noise is, well, in this case, I'm assuming we've got a scalar measurement. It works in non-scalar measurement, but let's say it's scalar. Then this is also just a single parameter that characterizes the measurement noise. And you can show that all that really matters is the ratio of those two. That if you double the process noise and double the measurement noise, you'll end up with the same estimates. You know, there's a subtlety around how these are related to the initial state variance, but brushing that aside, in steady state, all that really matters is the ratio of these two. And so you can set the measurement noise to a number and then just dial in the process noise. You've got one knob that controls how quickly you allow your coefficients to adapt. So really beautiful adaptive filter. And it's one of the things that just never would have dawned on me in the way it was taught when I took the class. I never would have thought that the measurements, you could put past values of the measurements in your H matrix or as part of your model. And that was the sort of big aha for me, is that when you're thinking about this linear model, H of n can be anything you want. And that includes being a vector of the past measurements that have been observed. There may be a technical violation here in that the measurement from one time step to the next, the noise is supposed to be uncorrelated or white. And I wonder if there's any problem with this being stochastic rather than deterministic. Eric, do you know on that? Is there any problem with the fact that what we're sticking in H of n is not, we can observe it, but it's not really fixed. It's really something that's stochastic. There's additional variability that we're putting in there.
I mean, time varying is fine, but
Right.
I haven't thought about it. It affects the noise correlation.
Yeah, I haven't either. Well, in any case, it's done and it works. It passes the engineering proof. And so the idea of thinking of the state as being coefficients and the H matrix, in this case a vector, being just a tap, a delay line, or a window of the past values of the measurements that you've observed, is sort of the big insight here. And then the process model is straightforward. It's just a random walk process for your coefficients. So again, this turns out to be a really nice adaptive filter.
Observation. The Markov model doesn't have any sideways arrows on the lines.
Yeah, I'm with you.
States mark.
But the measurements aren't supposed to cross over either for it to be Markov, right? Even if the state is Markov. Yeah, I need to think about that some more, Jeff. I think you might be right. I don't know the answer off the.
We don't have that same, it doesn't have to be a Markov model. We might have that, we had that rule for particle filters, but not for Kalman.
We do have the rule for the Kalman filter. Did we violate it?
Because you had past values of y, which means...
Example. Here is, for those of you that remember this, a pole zero diagram of a discrete time system that I'm going to excite with white noise to generate the observed signal. And one of the first things that you should notice about this pole zero diagram is that the system is not an all-pole system. The x's are where the poles are, and so it's got 5 poles, one on the real axis, but it also has some zeros, and that's a violation because the model we're using assumes that whatever you're modeling, that it is an all-pole system, and so I've deliberately got a mismatch in this case between the process that's generating the data and the state space model that I'm using to track it. Because there are these 2 zeros here. I don't know how many of you have looked at a pole zero diagram recently, but the way to think about this is in the frequency domain, if you're thinking about how this amplifies and attenuates at different frequencies. This is DC, and as you go around this upper perimeter and you get out here, you get to half the sample rate, the fastest frequency you can see in discrete time. And as you go around the unit circle, you should be thinking about your distance to poles and your distance to zeros. When you get close to a pole, so frequencies around here, it'll amplify the response. So if we're driving it with white noise, you'll see more power at this frequency that's a little bit more than pi over 2. And we'll see more power at this also. So you would expect to see 2 peaks. If you're looking at the power spectral density, you would expect to see 2 peaks at relatively high frequencies. Similarly, when you get close to a 0, it will attenuate more at frequencies where the distance on the pole zero diagram is close to a 0. And in fact, the response can be shown as a product of the distances to all the different poles and zeros, where you've got zeros in the numerator and poles in the denominator. And so usually when you get close to 1, it will dominate, and all the other terms will be insignificant compared to that one. So there should be an attenuation of power at these 2 frequencies and an amplification power at those 2 frequencies. So that's what it represents. And again, I'm just driving this system, this discrete time system, with white noise. And so that's what we expect. This shows the output over merely 100 samples of what the system produces. And sure enough, you can see some high frequency oscillations where it's being, the poles are causing those high frequency oscillations that you see in this. It's not like white noise, it's not random. You can see a high frequency pattern to it in time domain. This shows the true power spectral density. And it shows it on both a linear scale and on a log scale. And I'm showing it on both scales in part to make another point. First of all, notice that sure enough you get the two peaks due to those two poles. And one pole is apparently a little bit closer to the unit circle and causes a higher amplification at the higher frequency. Usually when you're doing signal processing, it's much easier to see where power is than where it isn't. It's very difficult to see the two zeros over here. And if you think of the power spectral density as a decomposition of how the power of the signal is distributed across a range of frequencies, then it's not hard to imagine that if there's very little power here, but it's far less than what you've got elsewhere, it's hard to see that. And in part because whenever you estimate the power spectral density, there's a blurring that occurs across frequency. You can't estimate at a frequency perfectly. All the estimates will cause some smoothing and will essentially fill in those holes. And so it turns out that the zeros don't have a lot of consequence, even though theoretically there's much less power at those frequencies. It rarely matters. What matters much more is where the power is located rather than where it isn't. This shows an example of a what I call non-parametric spectrogram. This is essentially taking a moving window and estimating the power spectral density based on that moving window. So this is not using a Kalman filter or any other type of adaptive filter. This is just what you get when you estimate the spectrum using roughly the equivalent of a zero-padded FFT with a moving window and appropriate other signal processing. And so you can see over time across, and I don't remember what my sample rate is, even though this says minutes, but this is a fair amount of data. And you can see on average you don't see clearly two bands or those two poles, the impact of those two poles. You certainly don't see. This is what we get when we apply the Kalman filter, and then at each time, based on those coefficients, convert those coefficients to the estimated power spectral density. And I initialized all the coefficients to be zeros. So it starts off with perfectly dark blue, can't see anything, and then you can really nicely see how as time goes on, it places the poles at the appropriate locations on the unit circle and gets them closer and closer until you get more or less a steady state estimate of what the power spectral density is. This pole is continuing to get a little bit closer and a little bit higher, but it's more or less locked in over in, I guess on this scale, 10 minutes over not a very long period of time. And I apologize, I don't remember what the sample rate was in this case, but isn't that cool? And if it changes over time, the filter can adapt because we've got this random walk model in the coefficients. So if suddenly there's a change, we'll see an example of that, then it can adapt and shift and adjust the coefficient. As I go through these slides, what I'm increasing is Q. So I'm allowing the coefficients to change more rapidly. When you do that, you should see more variability in the spectral estimate. And essentially what we're trading is variance of the estimate. Here we see more variability, it wanders around more, the coefficients are less stable than they were, in exchange for responsiveness, or, if you will, less bias. So we'll see it's less smooth, but it can track changes more quickly, allow the coefficients to change more quickly. And here's another example where coefficients are changing even more quickly. And I take it to extremes. One of the things I really like about using the Kalman filter as an adaptive filter, some adaptive filters become unstable when you are adjusting the one parameter that controls how quickly it can adapt. But over a very wide range of the equivalent parameter for the Kalman filter, the covariance on Q, it remains stable. So it remains stable over the full extremes. It becomes more variable, but it doesn't blow up and give you infinity or something else that's unreasonable. And so as it changes even more, then more variable back, but still more or less concentrated in the right place. So these are over many magnitudes of range. And then to see how well this tracks, I wanted to give it a chirp as well. And this is the non-parametric spectrogram. So this is the sliding window FFT of a chirp signal where I ramped it up and ramped it down, ramped it back up, and ramped it down again, just to see how well mapped in time. And so starting off with a very small value of q, only allowing the coefficients to change very slowly, you can actually see really cool, really nicely what the different poles are doing and even how many poles I had. I didn't specify how many coefficients we were working with, but here you can see one pole, it's trying to increase, but it can't increase rapidly enough because I've made the q so small. And so you can see it sort of fade out here, where it doesn't change in its frequency, but changes in its amplitude. So it doesn't, it can move sort of, its angle around the unit circle stopped moving, and it just moved away from the unit circle towards the center at that point. And a second pole went up and did more or less the same thing and sort of stuck at that frequency, and another one went up, another one went up, and then finally this one went all the way up and then sort of stayed. And then when the frequency started to go down, this one that was starting to get big starts to fade away, and then this one gets big and it starts to fade away. And you can see what's happening with the poles if you study this carefully enough. And this is an example where I'm not allowing it to adapt nearly quickly enough, and so it's not a great estimate, but you can still sort of see the spectral estimate of the actual. As we turn Q up, it gets better and better. These are able to last a while longer. They're able to move along the unit circle a bit more, and they're able to fade more quickly, as you would expect, after you think about it. And then, higher value of Q, now it's able to track much better, especially once we get up to here. And it is trading off between different poles, but those poles are able to move along, and it's doing a nice thing now. It's a causal, the Kalman filter that we've been talking about so far. You didn't talk about smoothing, did you, Eric?
I did in the linear. I did linear smoothing.
Okay, well in this case I'm not using smoothing, so that's what causes the sort of shadow to the right and why it's not on the left. It's not going both ways, it's just a causal. And as we turn Q up, it gets better and better. And this is probably about as good as it gets. There's still some sort of shadow over here because the frequency is changing, and the assumption is that it doesn't change. It's really tracking nicely there, as high as I could turn it up. And at this point where it turns around, suddenly there's a big error, and there's a few strange things that happen, but it very quickly forgets that and moves on and starts tracking what the new one is. So very stable and does a great job overall tracking, even in this case when the true content was changing over time. So it's just the linear Kalman filter, and you would think it's linear. What good is that? Everything I work with is nonlinear. But here's an example of a very powerful adaptive filter that you can use for almost any adaptive filtering algorithm that just uses the linear Kalman filter recursions. It doesn't require any of the more complicated things that we've been talking about. So any questions on that?
It's kind of funny how the strange discontinuity only happens, or it's much more pronounced when the frequency starts to drop at the upward apex of the chirp.
Yeah, I hadn't noticed that before. That's a good point. Yeah, so we see it here and here, but not here for some reason. Yeah, I don't have an explanation for that, but that's a good observation. It may have something to do with the way the signals were stitched together. I haven't studied right there, but there may be a discontinuity right there, whereas there may not be one right there. All right, well, so with that, why don't I turn it over to our guest speaker. So, as I mentioned, Mahmoud El-Gahari has joined us. And Moody, you might want to take, let's give the guys maybe 5 minutes as a break, and then you can begin. And we'll do it that way. But as I mentioned, Moody is one of my PhD students, and he's been working on joint angle tracking, and has done a lot of work with state space methods. So he'll be sharing with you what he's been working on, and some of the insights maybe that you've gotten as well. Did you bring your laptop?
I didn't, but I have a flash drive. Does this computer work?
I'll bet you can get it to work. If not, I imagine someone would be willing to loan you a laptop as well. Anyone want to loan Moody a laptop rather than trying to get this fired up?
Well, I sent mine in first for repair and they screwed up the red channel, so I don't have red. It's probably not a good idea. I only see blue and green. Yeah,
I've got a laptop in my office you can use.
Oh,
Let's do that.
mine's Mac.
So I can see those green.
I don't know.
You can use
I use this on the Mac, so.
You can use mine.
Thank you, Jeff. I think that'll be a little bit easier. All right. Well, thanks, guys, and I'll see you on Wednesday. So, as soon as you set up 5 minutes or so, we'll go ahead and begin. Thank you. No. I'm sorry. This meeting goes until 3, and I've got another meeting. And, yeah, I'm booked up. I think. Yeah, I will on Wednesday. I'll be here on Wednesday. And we could arrange to meet on Wednesday morning too if it's urgent. Tomorrow I'm picked up. But email me. You can email me. No, he was doing this for a while. Yep. for asking.
Knee bag, try that one more time. Okay, 3:30.
Great. Yeah. Thank you. That one's not allowed, huh? It looks like. Were the name tags here, or did you bring them in?
Yeah, the name tags were on the chair.
So someone's already chosen where I'm going to sit, apparently. Okay.
James?
Yeah.
You are in this group somewhere. Don't call the name tag. It might be under the...
Sitting on his name tag.
Is this you? You can join. Oh yeah, please do.
It is me.
Awesome. That was a good guess.
I'm the original James, actually.
Okay, you're just kind of the utility James, whatever name.
Apparently.
You can take one of these.
Yeah.
Larry's here.
Larry's here. Oh, sorry, I almost gave your chair away.
This one's okay? All right.
Interesting info. All right. But how is re-entry?
And then when you turn